morning. We shall continue with our lecture on crystal defects in metals, and last class we introduced the concept of stacking fault. See, so far we have been talking about dislocations which are perfect. That means that Berger vector is equal to the Berger vector has the least in particularly in face centered cubic crystal, the Berger vector of a perfect dislocation is A by 2 110 type, but we found out that energy of this type of perfect dislocation is more than partial, and we also showed you with a hard sphere model that it is much easier to move with the help of partial displacement or partial displacement vector. In fact, what we said is in face centered cubic crystal, the different layers are arranged in the fashion which is shown over here, and if we consider the first layer as a layer A, say this layer as A, and on the top of it we put another layer of similar hard sphere. So, these sides are called B, these sides are B sides. So, obviously, what you find then when you place an atom on the B side, part of this C is blocked. So, you can't put an hard sphere over here, and so and if you have a situation like something like this, you have in the next layer, part of that next layer is occupying B position and part is occupying C position. Now, you say C position is like this. The next B position here is you have an atom here. Now, you can't keep an atom here, this is C. So, but you can keep an atom here. So, basically this is that perfect dislocation Berger vector. So, what is happening is as if this movement here, this atom has to go over the sphere, part of the sphere, whereas instead of going like that, if it moves through the valley, it is more energetically favorable. So, that means this perfect dislocation is split up into two partial, one like this, another from here to here like this, and these are called partial dislocations, and their Berger vector is of the type A by 6 to 1 1 kind. So, if this plane is 1 1 1, then the Berger vector will be lying on the plane. So, that condition should be satisfied, that this direction should lie on this plane. And similarly, you can find out this Berger vector, you can find out this, and you will find that angle between these two will be 120 degree. So, on this plane you can have three vectors of Berger vector of this type, one this, another like this. And same thing which is shown over here, and it was shown that if this perfect dislocation splits up into two partial, which is shown over here, and then you calculate the energy which is equal to square of the Berger vector. So, in this perfect dislocation energy is A square over 2 and partial dislocation energy is A square over 6. So, 2 of this if you add up, this is A square over 3, which is less than A square over 2. So, therefore, this is energetically favorable as well. Now, what happens if such a partial dislocation exists in a face centered cubic structure? In a face centered cubic structure, you can visualize that this 1 1 1 plane, this is a closed back plane. So, this is 1 1 1. If we call this as layer A, the next layer on top of it, you can make it by joining this. So, this is the second layer, we call this layer is B, and the third layer passes through this corner, which is the layer C, and this sequence is repeated A, B, C, A, B, C. Whereas, we recall that in a hexagonal structure, the sequence is A, B, A, B, A, B kind of thing, or A, C, A, C, A, C kind of thing. Now, here imagine that here such a thing has happened, a part of a number of atoms, say these two rows of atom, they have moved through one partial vector, Baja vector, which is shown over here. It has moved from this point to this. So, that means this layer has now B has moved to C. So, which is shown over here, B has moved to C. So, it will be bounded, a part of this has happened, I mean in this region. So, it will be bounded by two dislocations, which is shown with an opposite sign. That means, it need not be exactly opposite, but the Baja vectors, they will be subtending some angle, and for simplicity we have represented it as an edge component. Now, this is where the stacking sequence is disturbed. What has happened is you can see that instead of that B layer moves to C, and C layer will move to A. So, this is how it has changed. So, if this part of the crystal, it has undergone that kind of a partial movement, displacement. So, this becomes C, this is A, this is B, this is C. So, that way. So, now you look at the stacking sequence, here it is A B C, A B C, but look at across this, what do you have? C A C A, which is something like a part is repeating like a hexagonal stacking. So, this fault or in that stacking sequence is called stacking fault, and so that means we can consider that this fault to be a two-dimensional defect. So, across this area there is a fault in stacking sequence, and we call this stacking fault energy, and these partial dislocations are known as Shockley partial dislocation, and the generation of Shockley partial induces a fault in stacking sequence. Now, this stacking, if there is a fault, there will be an energy associated with it. So, there is a surface defect, it has an energy, it is something similar to surface tension. But these partial dislocations, they are mobile, they can move on this glide plane, the glide plane is fixed. Now, this is a pictorial view of the same thing. So, here this is the part where a stacking, there is a stacking fault has been created over this zone. So, there is a partial dislocation here, there is a partial dislocation here, which is diagrammatically represented here. A part of it, say somewhere on this side, the two join and it is a perfect dislocation, but here we have two partials which is shown here. So, it means that this side is yet to slip, or here this side is slipped, this side has undergone partial slipping and this side is yet to slip, because dislocation we remember that is a boundary between slipped and unslipped region. This portion is slipped, this is yet to slip, whereas over here there is a partial slip, and this is represented like this, and these two vectors they are like this, and approximately what we can say, there will be a repulsive force acting between the two, and which can be calculated like this, G B 2 dot B 3 over 2 pi d, where d is the distance between the two partial, and this will be determined, that distance will be determined by the magnitude of stacking fault energy. If the stacking fault energy is high, this distance between the separation distance between the two partial will be low. Now, Shockley type of partial can be created by through slip. There is another way a partial or stacking sequence can be disturbed in a face centered cubic crystal, which is shown over here. So, at any temperature you have some vacancy in the lattice. Suppose if some of this vacancy, if this concentration of vacancy is more than equilibrium, which can happen if you suppose heat a piece of metal to a high temperature, and concentration of vacancy is a function of temperature, and then if you quench, then suddenly that entire that total number of vacancy cannot eliminate itself. So, there is excess vacancy, and this excess vacancy can condense or can accumulate in one of the slip plane, and which is shown over here. If they accumulate on B plane over here, this has accumulated. So, there what you have, because of the accumulation of vacancy, excess vacancy which have accumulated here, you have an edge dislocation created, something like which is shown by this symbol, and the Berger vector of this is perpendicular to the plane, and which is shown diagrammatically over here. This is the plane B, and on the plane this is where the dislocations, the vacancies have condensed and coalesced, and this has a direction, this has a sense which is marked over here. This is a positive sense, and then this is the Berger vector. So, it is this Berger vector is perpendicular to the dislocation line at every point. So, this is type of dislocation is a pure edge dislocation, and this pure edge dislocation it will, and we know that edge dislocation can slip only on one plane that contains that dislocation as well as the Berger vector as well as the dislocation. So, here the plane is not a flat plane, it is basically a cylindrical surface, and cylindrical surface which is not necessarily a slip plane. So, therefore, this type of dislocation is called frank, this type of dislocation is immobile, and it is called frank partial dislocation. Now, why partial? Because if you calculate its vector, basically displacement, on this side a layer, this B has gone to C. So, this part has been moved over here, or this has basically to this distance, by this displacement you do not come to occupy that similar A site. So, basically we can calculate this Berger vector. This Berger vector will be direction is perpendicular to the closed packed plane, and closed packed plane in this case is 1 1 1, and this Berger vector is equal to A by 3 1 1 1, A by 3 1 1 1, and distance between two 1 1 1 or closed packed plane in face centered cubic crystal is equal to A over root 3. This distance is A over root 3. And this type of dislocation, as has been mentioned, is immobile, and we also in dislocation a terminology is used is sessile, while Shockley dislocation partial is glacial, can glide, it is glacial, and this cannot move, this is sessile. Now, let us revisit that Lohmer lock, and in terms of what happens, this Lohmer lock we considered formation of a Lohmer lock when two dislocations moving on intersecting slip plane, if they join together along the line of intersection. In that case, a certain type of dislocation reaction can take place, which is shown over here, and this also this is accompanied by reduction in energy, because here this Berger vector square, it is a square over 2, this is also a square over 2. If you add the 2, it is a square, whereas the product dislocation energy is a square over 2. So, therefore, this is energetically favorable, and look at this, this is lying along that line of intersection. So, that means it is basically it is lying along the intersection, and its Berger vector is a by 2 1 1 0. If you calculate this line of intersection, and the line of intersection is 1 bar, intersection line of intersection of plane 1 1 1 with 1 bar 1 is 1 bar 1. So, therefore, character of this dislocation is edge dislocation, edge character, and it can move on a slip plane. You can calculate the slip plane, which comes out to be 0 0 1. So, dislocation slip plane is this, which is not a normal slip plane in a face centered cubic crystal. So, therefore, dislocation is immobile. Now, what happens if the crystal has a low stacking fault energy? So, instead of this perfect dislocation, it will be made up of 2 partials. So, in that case, which is shown over here, they are made up of 2 partial, and the leading partial when they interact, which is shown here, this leading partial when they interact, you get another partial dislocation, which is a by 6 1 1 0. The character is still same, it is edge character you can show, but look at that energy. This is also energetically favorable. It is accompanied by substantial reduction in energy, and this type of lock is associated with a stacking fault lying on here as well as here. So, what happens when this type of lock form? It will inhibit further movement of dislocation on this plane. Say, if another dislocation is generated somehow on this plane and is trying to move, this dislocation will try to repel. If it is similar character, it will try to repel that. Similarly, a dislocation moving on this will be repelled by this. So, that means whenever this type of lock is generated in the crystal, it makes dislocation movement difficult, or it makes the material stronger. We call this in technical term, the material undergoes strain hardening. Let us look at what is the effect of stacking fault on cross slip. Take up a 2 case. These are 2 intersecting slip plane, let us say, and here on this plane somewhere here, down this plane somewhere here, there is a dislocation barrier, something like, let us say, a Lohmer lock is there. And whenever and let us consider these 2 partial dislocation, which is separated by a faulted region, and character of this dislocation had it been perfect. So, this is the Berger vector of the perfect dislocation whereas the Berger vector of this partial is shown over here, this, and the 2 resultant of the 2 is parallel to the dislocation direction. Now, here when it is moving, it comes across this dislocation barrier, it cannot continue its movement along this direction on this plane. So, what is the alternative? Alternative is there may be another slip plane which intersects this slip plane somewhere here. It can possibly cross slip onto this, but only screw dislocation can cross slip, and for that to happen you have to apply a stress high enough, so that these 2 partials they join together, become a perfect dislocation lying along this line along this line, and when this becomes a perfect dislocation, this can cross slip onto another the cross slip plane. So, effect of stacking fault energy on cross slip is, if the stacking fault energy is low, the dislocations are separated by a large distance, you have to do additional work to join the dislocation together. And in other extreme case, if the stacking fault energy is high, in that case situation is something like this. So, here the work to be done to join the two dislocation will be less. So, therefore, what we can say that whenever in material where the stacking fault energy is low, there cross slip is more favorable. The deformation by cross slip, you can say this gives an additional mode of dislocation movement, or you can say this contributes to strain softening, whereas formation of lock contributes to strain hardening. Now, we have just seen how when one dislocation meets with another, they interact with each other, and there are very large number of such interactions are possible. We looked at few of these. We looked at formation of Lohmer lock, and when these Lohmer locks are associated with stable, this lock is much more stabler, and this type of lock is known as Cottrell Lohmer lock. So, this is one kind of interaction. We also looked at interaction when a dislocation is moving on a particular plane and it intersects the dislocations which are perpendicular to the plane, and in that case what we have is a interaction with a forest dislocation. So, in that case it forms jogs and or steps in the dislocation line. It can form jog and kink, while kink can glide, but jogs cannot glide, and if this jog will exert a resisting force on the dislocation. So, formation of jog also leads to strain hardening, makes it difficult for the dislocation to move, but formation of Lohmer locks will contribute, its contribution to strain hardening will be even more. And there will be many such possible interactions, and these interactions can be very easily visualized if we consider say a geometric construction, something which is shown over here. So, this is, we consider these interactions primarily only for face centered cubic structure. In a face centered cubic structure, this is, you can say, you imagine this is a crystal, is a cube, single crystal, and look at how these 1 1 1 planes are made. So, this is 1 1 1 1 plane, this is another 1 1 1 plane, this is another 1 1 1 plane, and this is the fourth, and these 4 slip planes 1 1 1 type slip plane, they make one tetrahedron which is shown over here, and they are designated, this vertex of this tetrahedron as designated at A, B, C, D. Now, here each of these sides represent a perfect, you can say the dislocation of Berger vector of type 1 1 0. This direction is represented by, this is 1 1 0. So, each of these edges are like that, and it is possible to find out or write down this indices of each of these plane and direction, and you can try it yourself, but in this slide it is shown over here, this vectorially what are their magnitudes, like B c is A over 2 1 0 1 bar, and these planes the indices will be different, and these planes they subtend an angle between them. You can calculate the angle between these 2 1 1 1 plane, and this angle it is easy to calculate. This angle will be close to around 55 degree, and different types of dislocations can be represented in terms of this tetrahedron, which is called Thomson tetrahedron. Like these perfect dislocations, these edges of the tetrahedron, they represent perfect dislocation, Berger vector of perfect dislocation. Now, a perfect dislocation on a slip plane breaks down into or dissociates into two partials like B delta delta C. So, these are known as Shockley partial, and whereas you think about Frank partial dislocation Berger vector is perpendicular to the 1 1 1 plane, and you can imagine you can drop a perpendicular say from C vertex C to the plane C, which is just opposite facing C. So, that means it is lying on this particular point here. So, these are called Frank partials. So, now it is much easier to write down different and visualize the dislocation interactions using this type of representation. So, one of these it is quite easy, say this is look at this a dislocation moving in one of these plane, say suppose AD. So, AD it breaks into two partial D gamma gamma A or gamma D or A gamma gamma D, A gamma gamma D, these are the partial. And imagine another which is on this plane, C beta and C alpha, C beta C alpha. So, C beta C alpha, and here see basically if you look at say similar another intersecting plane, and then they can interact and get a this kind of a dislocation B beta alpha, and these are perpendicular to the edge. Beta alpha is perpendicular to the CD axis. So, this is the way when you can visualize the dislocations to interact. Now, we also mentioned that dislocation when they are moving on a slip plane, they interact with dislocations which are threading. Say suppose a dislocation moving on this slip plane is intersecting with a dislocation which is threading through the plane. In that case, a step is created which is shown here, and one of the steps, say suppose this dislocation is a screw dislocation, and this step, this is a jog which has come out of the slip plane. So, this character is a Berger vector and this location is moving along this. This is the Berger vector of this dislocation. So, this component is edge component. So, if this screw dislocation continues to move along the slip plane, it will leave behind, it has to drag the jog. So, if it drags the jog along with it, it will leave behind a trail of vacancies which is shown over here, and this vacancy will exert a force on this dislocation and which will lead to strain hardening. But there can be extreme other cases, this jog, this length of the jog is very large. In that case, these two ends of the dislocations, they are rather free to move, which is shown here. In that case, it forms a dislocation dipole, and this is one way of increasing the dislocation length. You look at that how substantially through this movement of this dislocation, how the dislocation length has been increased, and we will see shortly that increasing length of the dislocation means also means that the strength of the dislocation goes up, it will lead to strain hardening. So, dislocation, as we have seen, say if you have a perfect crystal, then the crystal is very strong, supposed to be very strong, but presence of dislocation makes it weaker and makes it amenable to plastic deformation. But if you continue to pump in and generate more and more dislocation within the crystal, again the crystal becomes hard. So, dislocation can explain both it can explain why real crystals, the yield strength of real crystal is low, and why when we deform it, as the number of dislocation density increases, there will be lot of dislocation interaction, and which will make it strong. Now, let us see that if the crystal is perfect, how dislocations are generated within the crystal. Say suppose if you imagine this is a perfect crystal, there was no dislocation, and to generate dislocation you will apply shear stress, which is shown. And now, with the application of the shear stress, imagine that two screw dislocations of opposite sense. So, this is the positive direction here, this is the positive direction for the other one, and so this type of two edge screw dislocations are created, and they are separated by a small distance x. In that case, what is the energy of this type of configuration? Now, we know that energy of a dislocation, that is equal to G B square over 4 pi ln x over r naught. So, what we imagine that dislocation when it is created separated by a distance. So, then x and r 0 is the core dislocation core. We can assume that this dislocation core size is of the order of Berger vector b. So, this is the energy, elastic stored energy of the dislocation. Now, subtract the work which is done to separate or to create the dislocation. So, tau is the force, and you need to move the dislocation by a then the force on the dislocation is tau b, and you are moving the dislocation by distance x. So, this is the work done. So, this is the total work done. Now, if you differentiate and find out what is that maximum energy which has to be supplied to create this pair of screw dislocation of opposite sign. So, you differentiate this, and then we can say that to find out its maximum value, at what separation distance the magnitude of this energy is maximum. You differentiate it, equate it to 0, then you will find, with a little algebraic simplification, you will find the critical distance of separation is equal to G b over 4 tau. You substitute this back into this equation, you get this. And now, for spontaneous generation of dislocation, we can say that for this process to be spontaneous, this energy should be very low or approach or become 0. If you put this condition, in that case this is ln g, or you can say g over 4 pi tau will be equal to E, and so therefore, tau is given by this, and approximately you can say that shear stress needed for homogeneous nucleation of dislocation is of the order of G b over 30. So, which is very high. So, therefore, to generate dislocations, this is not possible. I mean, if the material is perfect, this cannot, it is impossible. You can say this also says that a perfect crystal will be very difficult to deform, because to create a dislocation there, you need to apply very high shear stress. So, since homogeneous nucleation of dislocation is impossible, then what are the dislocation source in a real crystal? Now, one source which is shown, which we will talk about, this is because say suppose these dislocations are not necessarily straight, and the dislocation lines may be curved, and this extent of curvature will depend on the magnitude of the stress that you apply. And it is possible to derive an expression relationship between the line tension or between the applied shear stress and the radius of curvature of the dislocations, and which is shown over here. We know that dislocation has an energy associated with energy. We can visualize this to be a, you can say, as a vibrating spring kind of thing. If you have an elastic string, you are pulling it, you can visualize dislocation to be a similar line, a line on which you are applying a tension. Now, if you apply a stress on the say suppose this is a string and you are applying a stress, then this will try to bend like this. Something similar is happening, which is shown over here. This is the dislocation line, and we can say that along the line there is a tension, line tension acting on it, and this is the stress which has been applied to the dislocation. So, this is the force which is trying to bend the dislocation, and when the dislocation bends, its length increases, and since it has a line tension, it will have a natural tendency to shorten itself. So, there will be a restoring force acting on it, which is shown here. If this is the tension and this is along, this is the tension, you draw a perpendicular here, perpendicular here, you can say this is the center of this curved dislocation, and this angle is theta. And if this radius of curvature is large, we can say this angle is very small, and this component, this horizontal component, is equal to t cos theta. So, you have an horizontal component acting in this direction, you have an horizontal component acting on this direction, and both will cancel out. They are equal and opposite, they will cancel out. So, net force on the curved dislocation because of line tension will be acting along this, and this magnitude is equal to twice sin theta, and if theta is small, we can say this will be sin theta is equal to theta. So, therefore, this restoring force is equal to 2 t theta, whereas the applied force is this. And now, let us look at it here. This length segment of this is S. So, now what you see here is the force acting on this dislocation segment is tau b. This is the force per unit length times dislocation segment length. This is the total force acting on the dislocation, and this is the restoring force. Equate the two, you can say equate the two, and remembering that theta is very small, this can be represented as S over R. So, basically this S cancels out. So, what you have is approximately it comes out to be T over R B. R is the radius of curvature of the dislocation. This shear stress comes out to be of this magnitude, and we know that line tension is approximately for dislocation is equal to 0.5 g b square. So, what we can say that tau is equal to half g b over r. Now, consider a case like this. You have a dislocation segment which are pinned here. So, this point cannot move and you have applied a stress. Now, here if it bends like this, then this tau, the applied stress, can be written as 0.5 g b over r, and this r you can say that center of curvature the center of this curved dislocation lies somewhere here, and distance of this center from this line is x. If it is so, then this r will be x square plus half L square root over. So, now you think about so that means this applied shear stress is a function of this distance of the center of this curvature curved dislocation line from this linear segment, from these 2 points. Now, what is the maximum value tau? When will this tau be maximum? Obviously, when this denominator is minimum, and denominator is minimum when x is 0. That means, center lies in between the these 2 points. So, in that case, what we can say that tau max value is G B over L. Now, considering that Berger vector, this is of the order of atomic spacing, say B is of the order of atomic spacing, say maybe it is 2 into 10 angstrom, 2 into 10 to the power minus 8 angstrom. And let us say this spacing is of the order of 100 atomic spacings. So, basically let us say 100 or 1000 atomic spacing. So, in that case, what is this? So, this is 2 into 10 to the power minus 5. So, G B over L. So, this is of the order of G over 1000. So, by this, so that means if this is small, then the strength of the crystal you can say that increases. If these dislocation segment is large, then the dislocation can be generated easily, and which is shown over here. Say when you reach this stage, in that case you reach a stage of instability. After that, in a little expansion, will form a configuration like this. Now, if you look at the character, this and this, they have character of one is a positive screw dislocation, another is a negative screw dislocations. So, they will have a force of attraction. So, ultimately they will join together and it will annihilate, and in the process what you will be left with, segment like this, and it will try to reduce its length. So, finally, it will come back to its original configuration and it will be left with a ring of dislocation. So, this type of source is a regenerative type. It generates a loop, dislocation loop, come back to its original position. With application of further stress, it will generate another loop. So, in this way, on the dislocation on that particular slip plane, a series of dislocation can be generated, and this type of regenerative dislocation source is known as Frank-Reed source. So, therefore, now what happens if this type of dislocation source are operating? They are acting on a particular plane, and several of these dislocations are generated. So, in that case, what you will have is you will generate a set of pile up, which is shown something situation is something similar over here, which is shown. So, here is a Frank-Reed source. You have a Frank-Reed source here, it is generating a dislocations. Now, it generates a loop. So, one side we have given a positive, another opposite side we have given a negative sign, and this dislocation moves until it meets an obstacle. Suppose the first dislocation which meets an obstacle, which is a grain boundary over here. So, it stops, it cannot cross this barrier. This is dislocation boundary, this grain boundary is a dislocation barrier. It cannot cross this. Imagine that it cannot cross this, then what will happen? The second loop which is generated will come close to it, but it will receive, there will be an opposing force acting on it, which will not allow the dislocation to come close to it. So, in this way a series of dislocation will pile up on the slip plane, which is shown over here, and when such a pile up formation takes place, it will result in significant strain hardening. Now, the question comes up, how many dislocation can you pile up, can get piled up within a grain or within this particular on this slip plane. Now, in a particular grain there will be multiple such slip plane, and which is shown over here. This is another slip plane. So, here also a pile up has formed. Now, the question is how this can pile up, can this pile up, is it stable or it can cross the dislocation boundary as well. Now, what will happen, this pile up, the dislocation at the head of this pile up will be subjected to a sufficiently larger stress. It is possible to calculate, and when the stress becomes large enough, it can initiate a another dislocation source to be operating here, and or else it can create a step and it can move into and generate a dislocation on this particular slip plane on the neighboring boundary. So, and when can this happen? It is possible to calculate this using that dislocation stress field, and we know that when you apply a shear stress on the material, that the force that is acting on the dislocation, this is equal to tau b. Now, imagine this dislocation pile up, which is made up of n dislocations. So, we can say as if this is made up, this is a super dislocation with a Berger vector n b. So, force acting on it is tau n b. So, this you can see that force at the head of the pile up, dislocation at the head of the pile up, the force acting on this particular dislocation is many times magnified. So, if there are 5 dislocations in the pile up, this will be 5 times the force that is applied on a single dislocation. Now, grain boundary, we can say assign a strength to the grain boundary. This is the critical stress which has to be exceeded, so that a dislocation is generated on this slip plane or on this neighboring grain, and the process of deformation can continue. Now, the question comes up, how many dislocations can you pile up within a grain? Now, this will obviously be determined by the grain size, and the number of dislocation that you can produce or say length of this dislocation pile up, there is a relationship between the length of the dislocation pile up and the number of dislocations, and which is shown over here. It is possible to calculate that using that concepts which has already been explained, but we will not go into the detail of it. Look at this nature. This is a factor which depends on the nature of the dislocation, whether it is a mixed dislocation or is a perfect screw or perfect edge. We can take that, assume that k to be 1, approximately we can take k to be 1, and in that case you see that length of this dislocation pile up is L. So, this is the length, which we can say approximately is half of the grain diameter, half of this grain diameter, and you can substitute this n over here, which is done over here, and if you take that grain diameter, the d over 2 is equal to L, then it is clearly it is seen that the shear stress tau which is needed for to excite dislocation source on the neighboring grain, it is inversely proportional to root over grain diameter. and this is the famous that Hall-Page equation. Now, so mind you, apart from this is the grain size effect, apart from this there will be the normal friction stress, say it is tau 0. So, this tau will be equal to tau 0 plus a constant of proportionality k over root d, and which is shown over here. So, in terms of this tensile stress, we can say that the strength of a polycrystalline material will be given by this type of equation. This is the friction due to the friction stress, the sigma 0, and this is the contribution of grain size or grain size effect on strengthening. This is k y over root d, and this equation is known as Hall-Page equation. So, that means what it says, if the grains are finer, the strength of the crystal or strength of the material will be higher. So, this is an important mechanism of increasing the strength of material. If you want stronger material, you make it the grain size finer. Now, with this, now we are in a position to go back and analyze, look at or find out the mechanism of deformation of single crystal. We recollect that this single crystal behavior or stress strain behavior of a deformation of a single crystal is shown by resolved shear stress strain diagram. And if we recall, there are 3 distinct stages. Stage 1, where there is very little strain hardening. Now, this is a single crystal, say suppose an orientation is somewhere here. Now, there will be a stage when the dislocation can move only on one slip plane. So, which is shown here. So, in this particular, as long as this orientation is within a triangle, it will move, it will have can slip only on one slip system. So, until it reaches this point, it will be moving in one slip system. So, that is the time only mechanism of strain hardening will be interaction with forest dislocations. So, that is why here the strain hardening is less. Now, when the orientation reaches here, you have multiple slip taking place, and when slip takes place on more than one slip system, then dislocation moving on one plane will interact with another, moving on dislocation on another, it will form Loma-Cottrell lock, and there will be large strain hardening. It will also lead to a formation of dislocation pile up, because it is quite likely that dislocation moving on one slip plane will reach the boundary, which is a barrier, or will reach a Cottrell-Loma lock, that is a barrier, and further movement is prevented. So, this is a situation. So, therefore, that is why this is where you have severe strain hardening, and the main mechanism of strain hardening is formation of dislocation locks like Loma-Cottrell lock and dislocation pile up. Now, finally, it is quite possible that as you go on increasing the shear stress, you will also reach a case, say where many of these dislocations, they may have this, split into partial, and when the shear stress becomes large enough, some of these partials they can come together and they can join and form a perfect dislocation, and if this dislocation has a screw character, it can cross slip onto another plane. So, and when this mode becomes operative, that cross slip, then there is some amount of strain softening, that is stage 3. So, with this concept or idea about that dislocation movement, that resistive force that dislocation experiences when it moves through the lattice, say it experiences resistive force because of the periodicity of this atomic arrangement, which is a you can say it is a Pearl stress or friction stress. Apart from that, it will also experience resisting force because of other dislocations which are present in the crystal, and they can interact, dislocations moving in different slip plane, they can interact, form different types of locks which prevent further movement of the dislocations, and this dislocation movement is also controlled by formation of surface defect like stacking faults, and which make which also contributes to strain hardening. And it can also depending on the magnitude of stacking fault energy and the applied stress, if a perfect dislocation, the stacking fault disappears, then the cross slip becomes possible, and which can lead to strain softening. So, this is how it is possible to explain the mechanisms of mechanisms of deformations of face centered cubic crystals. And deformations in other crystals also can be dealt in the same fashion, but I think it will be in that case we will be going into too much in details, and this is beyond the course, I think, of introductory course on physical metallurgy, but principles are exactly the same. And next class we will look at a little beyond, is where we will also see that dislocation so far we are taking it for granted that this is a defect which is there in the crystal, but are they there? Are there any experimental evidence, and can we calculate that what is the number of dislocations which are present in the crystals? Can we see the dislocations? And also we will look at certain specific dislocation arrangements which will simulate a grain boundary, and we will also look at the nature of grain boundary. Although grain boundary we have referred to number of times, that is also a surface defect, but there are some low angle dislocation boundaries can explain and give some idea about the order of grain boundary energy, but still it is still now exact nature of the grain boundary is still not known, but the concept of dislocation helps us to understand the nature of dislocation boundary, and we will take this up in the next